Hello, 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 and welcome back to another episode of Kerbal Space Programming. Kevin here, and in the last episode, I said that I was going to take a look at the tuning parameters that we had for our ascent function, and then I realized I don't want to do any of that. The whole point of programming stuff is that I shouldn't have to try out various launches and do this stuff over and over and over, and I realized we're coming up on, this is our 30th episode. Why don't we actually look at some artificial intelligence concepts and make the computer solve that whole problem of figuring out the right value for our ascent? So here we are, and this is a very important algorithm, and I've laid out kind of the baseline of what this does, and we're going to go through and we're going to build up an example, and this is called the genetic algorithm. So I'm going to walk through kind of what this is, and we're going to build this out in real time. So first off, we say we've got a local population that is some starting population. That'll have to be a function somewhere. We'll say that our current generation is 1, and then we've got this loop here. So we say until some ending conditions are met, we're going to do this loop. We're going to say for every candidate in the population, set a fitness score for that candidate, right? And then we're going to say, now we're going to create another variable that is the parents, and we're going to build that from selecting out of that population. Then we're going to say, okay, the children is based on the crossover of those parents, and then we're going to mutate the children, like Ninja Turtles. Then we're going to set the generation to the next generation. We're going to set the population to those new children. Now what this does, it's a very simple algorithm, but what this does is it goes through and it says we've got a couple of possible solutions to a problem. We're going to use a fitness function to determine how good of a solution they are. Then we're going to select a couple of those solutions using some sort of selection criteria based on that fitness function and decide those are going to be the parents for the next generation of possible solutions. And then we combine those parents in some way to figure out what the children should be, and then we may introduce some slight modifications so that we get some more variance and different possible solutions, and then we just run this over and over and over until we decide it's good enough. And so this is a very kind of general algorithm. We've got nothing in here that has anything to do with ascent. We could use this for tuning hoverscript. We could use this for tuning an ascent. We could use this for any number of things. What matters particularly for our use case is figuring out how we set this fitness score and how we decide to, how we select the things based on that criteria, how we go about merging two potential solutions into two new solutions. So basically parents have children, and then how we introduce some random changes to those solutions. And the reason this is the genetic algorithm is that it is based on traditional evolution. Your parents are really good at ice hockey, it's likely that you're going to be really good at ice hockey. Or maybe you got brown eyes from your dad and brown hair from your mom. And so we get some sort of crossover effect that the children are based off of both of those parents. And then there may be some small mutations. Maybe your genes weren't copied entirely correctly. And we just do this generation by generation. And eventually we end up with solutions that are much better for the problems that we're trying to solve. So if I copy this over real quick to the craft that I have on the Launchpad, I'm going to switch to the archive volume and I'm going to run genetics. And of course we get this error that none of these things are defined, right? So we're going to go through and actually build up something. What I want to try and do is we're going to call this guess the number, which is a pretty simple game. We're going to use a genetic algorithm to guess the number that we have in our head. So we're going to say target number is, as a constant, is 42, because that's a perfect secret number. It makes sense to me. So now, because we've got this algorithm here, and this is kind of the generic approach, we're going to start building out a bunch of functions to meet this specification. So I'm going to say function starting population, and this is going to need to return a list of possible candidates. So we're going to say local population is a list, and we'll return that population. And here we'll have to actually build some, right? So we'll build some candidate solutions. Now we've got, we've got ending conditions met, which is a function. And of course you could base when you want to stop on kind of anything, but I'm going to go ahead and say, let's see, this takes two parameters. It takes in a population and it takes a generation. Let's go ahead and say, well, return false by default, and then we'll have to figure out some condition. Let's just say if generation is greater than 50, return true. So we're only going to run this 50 times, and then whatever number it picks by that point is whatever it's going to be. So let's go ahead and now, what else do we have? We have set fitness score. And this is going to take a candidate. And we're going to have to do something to it. We don't have to return anything, but we're going to have to somehow update that candidate to give it an actual fitness score. We have a function selection. And we have a function crossover. And these are going to take parameters. Parameter parents. And parameter population. And we've got a function mutate. Right, okay. Let's see if this will at least run. And obviously, we're not really doing anything yet. We're just kind of making the skeleton for our application. I'll go ahead and copy this over real quick. And, oops, jump over and run genetics again. And unexpected token I found. Oh, right. Const. No, not const. We'll just set. There we go. Set that to 42. Yeah, we're not using that yet, but I'll just keep it there. And okay, so now we've got an argument mismatch. Oh, forgot to put something in the mutation. So parameter children. We're going to mutate our children like monsters. All right. And iterator. Now it's mad that there's not an iterator. What's it mad about? It's mad about... Okay, for candidates and population. So the reason that this is that we're setting the population to the children, which means that when we get our crossover, we actually need to return back a list. So for now, we'll just go ahead and just return back the parents. And actually, we can go ahead and do the same thing here. We'll return back the population. There we go. And copy that over. And we'll run again. And it runs. Okay, and it ended. And of course, it didn't do anything during that period. So let's actually add in some debugging here. So I'm going to go ahead and, actually, let's put it after we determine the fitness scores. And I'm going to go ahead and say print generation plus generation. Right. And I'm going to go ahead and print population dump. So this is just going to give us a descriptive output of what we're looking at. And then I'm just going to go ahead and say weight 0.1 so that things don't go crazy. And I'm going to go ahead and clear screen here as well so that we can see all of that and it doesn't get messy. Let's go ahead and run. We see, there we go. We're going through all of our generations and our population is just an empty list. So that's kind of boring. Let's go ahead and change that. So we need to think about what our candidate is going to be. And the idea with a genetic algorithm is that you have two things kind of associated with a problem. You have a chromosome, much like people do, and you have a fitness score at some point. So I'm going to go ahead and say from local I is 0 until I equals 4, and step set I to I plus 1, do. And now we've just got a loop here that's going to go 4 times. It's going to increment I every time it goes. We're going to go ahead and say local candidate is lexicon. So we're creating a lexicon, which remember is an associative array. So I'm going to go ahead and say set candidate fitness to -1. We're going to say -1 means that it's not defined yet. And I'm going to say set candidate chromosome to, and the solution that we're trying to figure out is to try and lock in that target number. So we're trying to guess the number. So I'm going to say let's take random, which is a random value between 0 and 1, and I'm going to multiply that by 100. All right, so it's going to pick some random value between that and 100 each time that it's creating one. And I'm going to go ahead and I'm going to say population add candidate. All right, and we can get rid of this now. So let's go ahead and copy that over and see what change happens. Okay, nope, it's mad because I forgot the dot. There we go. Copy this back over. And all right, okay, now we're actually seeing something. You can see that we've got these fitness scores that are always -1, and it generated these random numbers. Now, one thing that I actually want to change, just because we're trying to keep things simple, is I don't actually want these to be, I want these all to be integers. So we're just going to go ahead and say round this number. And if we go ahead and run this again, yep. There we go. Now we've got something that randomly picked 35, something that randomly picked 99, and all of that stuff. Now, okay, so this is great. We've got something that's picking possible solutions, and yeah, but it's not evolving anything. So we've got to start going ahead and doing that. So we've got a couple of functions that we haven't really prototyped out here. Okay, so we've got this, yeah, this generation test thing is there. And actually, let's go ahead and print out well, no, we've got to go ahead and figure out our fitness function first. So we've got set fitness score. That's great. Right now it's a -1 for our examples because we haven't assigned really anything. And the idea with the way that we're going to be doing this is that we want a fitness score that's going to be between, that's going to be above 1. So what I'm going to go ahead and do is I'm going to say set, let's see, candidate fitness to, and we want something that is going to get higher as we approach 42. So I'm going to say 1 divided by the absolute value of, what did we call that up there? Target number. Target number minus, and actually let's go ahead and split this out. We're going to go ahead and say local difference is the absolute value of target number minus candidate chromosome. All right, yeah, we're still, because I'm zoomed in, so I've got limited space to work with. So that's just the difference between what the current chromosome is. Now, a lot of times you would actually set up your chromosome to reflect things like the you'd reflect it to throw in a whole bunch of more information, but we're trying to keep things simple now. That basically the chromosome, because you think about humans, we've got, we've got 20 some chromosomes and they manifest in like, well, that actually means you have blue hair. Here we're saying a chromosome of 98 means that your guess is 98 when you're trying to guess the number. So we're saying that the chromosome is exactly what that is. So we would go about changing the fitness score if we were solving a different sort of problem. But okay, so we're going to get the difference. And actually, let me just call this diff, I guess. And we can avoid cutting off the screen. I'm going to say 1 over diff. Now, let's see. That's good. That should do it. The only thing that I want to change here is I'm going to say the maximum of either diff and 0.01. Because if we are exactly 42, then this would end up trying to divide by 0. And that would not be good. So we end up now setting the candidate's fitness to something that should get higher the closer it is to 42. Let's go ahead and save that and run that. Now we go, okay, so it's not evolving, but if we look at the scores, we've got something that guessed 18, and it got a fitness score of 0.04. We got something that guessed 4, and it got a smaller fitness score of 0.02. 67 was 0.04, so that's roughly about as far away from 42, but just on the other side. And that's exactly what we want. We just the fitness is just how good of a solution is this particular candidate to the problem that we're trying to solve. And that's exactly what we want. So that's great. Now we've got some sort of fitness score. Wonderful. Now we have to figure out how we're going to do selection and crossover and mutation. Let's go ahead and start with mutation. All right, so this is, all of these kind of have variants, but I'm going to go ahead and, because we're just dealing with kind of integers and we're just trying to guess the number, I'm going to go ahead and just say if random is less than 0.5, because remember it's between, not even that, not that much. If it's less than 0.1, so 10% of the time, because this is between 0 and 1, then I'm going to go ahead and say, oh, no, we're doing this for all children. So for candidate in children, if random is less than -1, well, then we're going to go ahead and do some mutation, because we don't want to go ahead and mutate absolutely everybody. We only want to introduce a small amount of change to some of the candidates, maybe some of the time, just to kind of shake things up and make sure that they don't all get stuck at a particular point. So I'm going to go ahead and say we're going to add or subtract a little bit depending, we've got to kind of decide that. So I'm going to go ahead and say, again, if random, and this time I'm going to say if it's less than 0.5, so roughly half the time. And then we're just going to say, add something, otherwise subtract something. And what are we going to do? Well, we're going to go ahead and say candidate, not fitness, but the chromosome. Well, we'll set candidate chromosome to candidate chromosome plus random times 3, but we will round that. Right, so this is going to go ahead and give us a random number up to 3. So between 0 and 3, if we got kind of heads on this half and half flip. Otherwise, we'll go ahead and subtract that amount. So there we go. Now we've got that, and all this is doing. So we're just saying roughly 10% of the time, and it could be that just because this random number generator is random, it never gets caught, or it could be that it gets caught more often. We'll either add or subtract 3 from this thing. And so if we go ahead and copy that over, we can watch this happen. And you can see that some of these values are actually changing. Not very frequently, but just some of the time. And they're, changing by just very small amounts. And of course, we're not doing anything to make sure that they get any better, but they are changing. So we are making progress. So the next thing that we want to do, let's go ahead and, we'll work from the bottom up here, is figuring out this crossover. So the crossover function takes in a bunch of parents and spits out a bunch of children. So let's go ahead and say local children is a list. And then I'm just going to say, not for, but from, local I is 0. Until I is, I equals parents length, step set I to I plus 1, do, and just, kind of short on space. And instead of returning parents, we're going to return children. And now inside this block, we've got to go ahead and say, all right, local parent 1 is, actually, we don't want to update by 1. We want to increment this by 2 because we want to get 2 parents, obviously. There we go. Local parent 1 is parents I, and local parent 2 is parent I plus 1. Actually, you know what, let's, just for the sake of understanding, let's just call this mom and dad, right? Mom and dad, because we're making child solutions from parents. So we've got mom and dad, and they need to make a baby, algorithmically. So how are we going to do this with these various numbers? I don't rightly know. Well, there are a couple of ways that we can go about. I mean, there are a bunch of different strategies that you can use to handle crossover of different strategies, but we're kind of restricted because we're dealing with integers. We could take the average, but that's kind of cheating if we think about it. That should make things a little too easy. So I'm going to go ahead and just say if random is less than 0.1, so 10% of the time, sure, fine, we'll go ahead and take the average. So we'll say, well, we've got to create a new candidate, don't we? So we're going to go ahead and say local, well, we'll just say child is lexicon. And we'll say set child fitness to -1 to show that, nope, we haven't evaluated this one yet. Okay, so 10% of the time, then fine. We'll say set child chromosome to the average of those two. Do we have average? No, we don't. So we'll have to do it manually. We'll go mom chromosome plus dad chromosome, and take all of that, divide it by 2. And then, of course, we'll want to go ahead and round that as well, because we're really trying to keep things simple and say we're dealing with integers. So 10% of the time, when we pick a mom and dad, we're going to get a child that just that is the average of those two. Otherwise, let's say half the time it's exactly dad and half the time it's exactly mom. So we'll say if random is less than 0.5, I'll just put the else there because we're going to copy paste a little bit. Set child chromosome to mom chromosome. And otherwise, we'll set it to dad chromosome. All right, so there we go. Now, the other thing, though, is that if we do this right now, we're going to discover that our population decreases very, very quickly. We need these parents to actually produce 2 children. So let's see, are we using I? Yes, we're using I. So I'm just going to go ahead and say, yeah, we could put a loop in here, but I'm just going to be lazy. I'm going to go ahead and copy and paste. Oh, no, I'm not. We actually need to do this twice. Yeah, so this stuff actually goes together. The last thing I forgot, though, is that we've got to say children add child. We've got to add to that list. And okay, we'll add another from here. From local j is 0 until j equals 2. Step set j to j plus 1. Do. And then we've got this block in here. So this will make sure that this whole thing runs 2 times, and we add 2 children for every pair that we're looking at. So we've got this this local I variable that's just an index on our parents. We're going to say take, mom is parent 0 and dad is parent 1, and the next time we're incrementing it by 2, so mom is parent 2 and dad is parent 3. And we'll just do that over and over, and then we return the children. So let's go ahead and see if that works. All right, now we see we've got some evolution going on here. They're merging. Of course, it's hard to really tell that just by looking at how this is going. But still, despite the fact that these things are combining, you can see now that we've got 2 of them that have the exact same chromosome. And, well, actually, we've got 2 pairs that are the exact same chromosome, which is something that we would kind of expect from the way that we're doing this crossover operation. And this is just a very naive mechanism for trying to get 2 new solutions based off of 2 parent solutions, but we can go ahead and kind of expand on that down the road. What's really important now is this final bit where we select the candidates of the population that are fit to be parents. So how do we go about solving this problem? Well, one thing that we could do is we could just say, all right, we'll just take the ones that are the most fit. We'll just say, all right, we're going to cut off the one that was furthest away from the right guess. But the problem there is that while it would work in this situation, if we're looking at kind of more complex problems, we're saying like an ascent control, and we had it trying to tune multiple different values, like we've got something that's handling the thrust limiter and something that's handling something else, well, then it could be that something is a little bit worse this time, but it has some really good partial solutions in it that we want it to make to pass on to the next generation. So instead of actually doing that, we're going to add, again, a bit of random chance, and we're going to make sure that it's more likely that the solution that scored very highly gets put into the next generation, but that it's still possible for a bad solution to make it through, or for a less good solution to make it through. So what I'm going to go ahead and do is I'm going to say set total fitness to 0, and I'm going to say for candidate in population, and we're going to say set total fitness to total fitness plus the candidate's fitness. So this is just going to get the overall total fitness of everybody in this generation. And then we're going to set that percentage likelihood that it will get chosen on the, we're going to set that on the percentage. So if you have a fitness, if your fitness was, 90% better than everybody's else, well then when we're looking for a candidate, you're going to have a 90% chance of getting in there. Now what we need to do is we've got to actually, return something other than population. So I'm going to go ahead and say local parents is list, and we're going to return the parents, because this function's job is to just determine who is fit to create children for the next generation. Now I'm going to say until parents length is equal to population length, because we want to return as many parents as we had in the previous generation. So that's what we need. And then we're going to say, okay, now we need to pick one at this point. I'm going to go ahead and I'm going to say local possible candidate is population, and we're going to give it an index. We could go ahead and just say loop over all of them, But the problem is then that's going to give unfair weight to the first guy in the list, right? And that doesn't make much sense. So I'm going to go ahead and say, let's see, round. Well, what I should say, what I want to do is I want to say population length times random. The problem is that's going to give us a float variable. And I'm not sure if I round if we might end up in a position where, let's see, if the population length, we can actually test this real quick. So the population length, we'll assume it's 3, right? And if we multiply that by 0.99, whoops, what? Right, because there's no period there. Print that. Okay, clear screen. Yeah, we don't want to round it, we want to floor it, because if we round this, if our length is 3, then that means that because things are 0 indexed, we could end up in trouble. So if we get this, then we'd try and access the index number 3, which is actually the 4th one, which doesn't make sense. So we want to floor it, yes. So we want to take basically just drop off the decimal point. So we're going to say, give me a random number between 0 and the length of our population. And that's the candidate that we're going to look for. And now we're going to say, we've got to figure out that percentage chance that we're going to go, yep, you're fine. We're going to say if random is less than, we'll just call this candidate. Why are we doing that? Right, okay. If random is less than candidate fitness divided by total fitness, that's going to be a value between 0 and 1 as well. Well, then we know, okay, then we can go ahead and add you to our list. So we'd say parents add candidate. So what this is going to do is we're going to say, all right, let's imagine that everybody has a fitness score of 4. And we've got 4 candidates, so the total that we're looking at is 16. Well, then the likelihood of you getting picked, this little bit in here, oh, come on, Kevin. What is with you today? There we go. This bit in here is saying, all right, your own fitness, which is 4, divided by the total, which is 16. Well, that's 25%. That's 0.25. We're going to say, okay, so you've got a 25% chance of getting picked, which makes sense, right? If everybody in that set of 4 had the same score, well, then you should have a 25% chance of getting picked. Then we'll generate a random number and say, if it's less than that, if we get a value that is below that, then perfect, you got picked. So this is how we're going to go about doing this. Now, we just do this over and over until the people that we've chosen until we've chosen as many people as we had in the initial population, and those are our parents. And I think, I don't want to be too hasty here, but I think we're pretty good here. The last thing I want to do is at the end of this loop, I want to go ahead and say clear. Well, no, it's fine because we're still printing it out. Okay, let's go ahead and run this. Let's tempt fate. All right. Now we've got all that stuff. Run genetics. All right, it's 25. Everybody's stuck at 25. Well, that's no fun. Everybody's stuck there, and all right, somebody got to, okay, we're at 26, 25 again. All right, so that wasn't great. We only got to 25. We're trying to guess the number 42, and after 50 generations, we didn't quite get there. I'm going to go ahead and say let's change our ending conditions, just for now. I'm going to say, let's, instead of actually tracking our generation, I'm just going to check the fitness of these candidates. I'm going to say if the fitness, let's see, for candidate in population, because you can decide to run this kind of indefinitely. You can decide to terminate it after so many generations or whenever the fitness score gets to wherever you want. I'm going to say if candidate fitness, actually let's just check the chromosome instead of even checking the fitness, equals 42, because we happen to know exactly what the right solution is here. We'll go ahead and copy that. Well, not if, we need to actually do something. Then we'll return true. True meaning yes, we should be done. All right, so we'll go ahead and copy that over and run again. And all right, we're at 4. We've got one at 43. Look, its fitness score is 1. That is awesome. Look at it. And wait, the program ended. Why did the program end? What was your deal? Why was your fitness score? You what? 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 Oh, you know why? Because it mutated and we didn't actually print it out. So yeah, okay, we should go ahead. Whoops. I'm gonna go ahead and copy this again. And I'm gonna go ahead and say final generation. And we'll get rid of that. And print the population again. And good. All right, let's run this one more time. Generation 1, 2, 3, 4. Oh, look at that. They're getting really close. They're so close. 43, 42, 43. There we go. All right. Final gen. Oh, and I wanted to actually, I'd like to know how many generations it took. It took. There we go. Oops. All right. Go. 43, 42, 40. Oh, undefined. Oh, yep, wrong. Typo on my part. Let's go ahead and kill that. Save that and go again. Generation 2, Generation 3, all of this random stuff. 13. Oh man, it's taken us a long time to get down there. We've got stuff stuck at 70 and 73 and 72. Part of this is because our parent merge stuff is actually very, very aggressive. Generally, you wouldn't have. We've basically got 90% of the time it's just going to pick one of them. And so we end up with a very homogeneous group of solutions, which means that it takes quite a while. Basically, we're relying on that mutation for anything better to kind of show up. And occasionally we see worse things that show up and then kind of track through. See, look, we're already at 135 generations. And, oh, come on, 68. One of you's got to get there. Come on, you can do it. Whew. Almost at 200 generations. And of course, this is going to depend on kind of the random number that was initially chosen. But we're relying now, because, even if we merge these parents, we take the average of 73 plus 73, well, we're going to get 73. So now it is entirely up to mutation to get these things right, which is part of why maybe we might want to add in some additional, 200, woof, man. This one is taking a long time. While that runs, I'm going to go ahead here and start tweaking some of these values. I'm going to go ahead and look at the mutation probability. I'm going to up that to 20% of the time. And I'm also going to go ahead and, well, no, we should change one variable at a time. Go ahead and do that. Really? You still? Yeah, it is not getting any better, is it? Oh, man. No, it's just, I think part of the problem as well is that our fitness score does not get incredibly better. Well, there we go, 74. It doesn't get drastically better, so the likelihood of picking a 74 versus a 76 is not very much, right? Because the probability is not huge. But we'll go ahead and kill that, because man, we got almost up to 500 and still didn't manage to get anywhere close. We'll go ahead and run genetics again with much more mutation happening. And okay. Well, there we go. I think one of them started off pretty quickly. It took 9 generations that time to get to 42. Let's run again. 32, 35, 36, and they're stuck at 30. Oop, come on. 39, 4. Oh, there we go. All right. See, we've got more mutation. That does seem to happen, or that does seem to help. One of the other things that we can go ahead and tweak is we can say, let's have more candidates in a particular round. So the starting population will go ahead and say, instead of 4 candidates, I would like 10 candidates. All right, so we'll go ahead and do that. And all right. Okay, 3 generations. Let's try that again and see if that was a fluke. 2, 4 generations. All right, so this is, a bit, part of it is, we've got a random number that's between 0 and 100. So when we have 10 options, oh, there we go. We got an error. What happened? I don't know what happened. Argument out of range. Argument out of range, but the thing was already done. It said it took 10. That is interesting. If you run it again, what's going to happen? 10 items. 3. Oh, man. They're all really, really close, and they're still not quite getting there. All right. There we go. 9 generations. So having more solutions to combine does make things better. You also see that these are not as heterogeneous. You have 43, you have 39, you have 42. We don't have that same issue of, the different parents getting selected. When you're selecting a larger population, there's a much higher chance that we'll pick out good candidates. I'm going to drop this back to, let's say, 6. We want it to be an even number so that everybody pairs off. Another thing that we could do, let's see, we've got this selection. We could change the crossover likelihood, right? So we could say, now this is going to be pretty obvious. If we change the likelihood of just averaging, we should get pretty close. If we say half the time we're just going to average, well, then we should get in even faster. So we run this. Yep, 3 generations. 4, no. Well, of course, now we're averaging and it doesn't much matter, does it? Okay, 21 generations. Ugh. We need more candidates. But on average, so this is the thing about genetic algorithms, is that you're dealing with a lot of randomness, and you're just dealing with the idea of selecting the best options, allowing some of the bad candidates to possibly stick around in case they have parts of their chromosome that are actually helpful, but just didn't happen to manifest in that generation. And you're dealing with it, and you're allowing it to just go generation by generation and make very slow improvements on a particular solution space. And this is one of kind of the big ideas of AI. Well, I don't know about anything about AI. This is a big thing in AI. And this is kind of the algorithm by which you can build a whole bunch of stuff. So what I'm going to do before the next episode is go through and say, I'm going to go ahead and use this to actually tune RSN profile. I'm going to say, you just go ahead and run and do k-universe revert and do that over and over and over until you figure out a good tuning value, because I don't want to be bothered. If we set a fitness score, we think about, basically what we're doing here is just figuring out a way to determine how good of a solution was that. And we could say, how much delta V did you end up with? How crazy was the periapsis relative to the apoapsis? We can, basically figure out a score that works for that, and then we can just let this thing run over and over, generation by generation, and make improvements over time until it finally settles in on a very good value. So I will be showing the results from that off in the next episode. Until then, I hope you are prepared for when the robot overlords take over. I'll see you in the next episode. Cheers.